This program is brought to you by Stanford University. Please visit us at stanford.edu.
Let's talk about conservation of charge a little bit. The most naive version is that the amount of charge in the world, whatever the world means, doesn't change. It just stays the same. That's the most naive version of it. Now, if that were all there were to it, then it really wouldn't say very much. If a charge disappeared over here and reappeared on Alpha Centauri at exactly the same instant of time, of course, we have to worry about relativity and the fact that same instant of time may be a little bit confusing, but let's get a little pre-relativistic. If a charge disappeared over here and reappeared on Alpha Centauri instantaneously, we would say charge is conserved by that definition, that total charge doesn't change. But we aren't on Alpha Centauri. It's too far away for us to know what's happening there. And so, in that sense, if that's all there was to charge conservation, it wouldn't tell us anything. It wouldn't tell us anything at all. Okay, if we could get to Alpha Centauri and check the charges there, we could go to Beta Centauri or Gamma Centauri or the next galaxy over or whatever, and we would have exactly the same problem that within our laboratory, charge conservation wouldn't mean anything. We'd have no way of checking it. Now, what is the way that we check it? Can charge disappear from the laboratory? Yes, charge can disappear from the laboratory. It can reappear outside the laboratory. But in order to do so, it has to pass through the walls of the laboratory. And so some detector set up at the walls of the laboratory to monitor the flow of charge what do detectors do? They would ring bells or detect. That's what detectors do. They detect. It would detect, ring bells, and we would know that charge passed from the inside to the outside. That idea that conservation means more than just the algebraic sum of the charges in the world doesn't change, but it means that there's a concept that when charge does disappear from a place, it identifiably moves through the walls of the system, through the boundaries of the system. That gets quantified in the idea of local charge conservation, or the idea of a current as well as a charge. A current is a flow of charge. So another way to say it is if charge disappears from this room, it's because a current flowed through somehow the boundaries of the room. That's the only way it can happen, and a current flowing through the boundaries of the room is detectable at the walls of the room. So let's see if we can quantify that, not just quantify, formalize it, turn it into a mathematical statement of some sort, and then check with our little theory that we made up about charge, we'll go back to it, whether it satisfies that criterion. All right, first of all, there's the concept of charge. Yes?
Is this particularly different than a similar statement about mass?
No, it is not particularly different than statements about mass. Now, the difference is that, I'll tell you what the difference is. Mass by itself in a relativistic theory is not a conserved quantity. Energy is the corresponding conserved quantity. All right, energy, and it comes along with another conserved quantity, or three other conserved quantities, which are called momentum. And they form a complex. But each one of them is separately conserved, and each one of them has a flow. Now, in fact, the momentum is the flow of energy. But what's the flow of momentum? And that's something else called stress. Now, whether we'll get to the stress, it's called stress, not the kind of stress that you feel when you know you've lied to your wife, but then she's going to catch you, but the kind of stress that a material object experiences when a force is imposed on it. Did I say something about having lied? And no, I didn't mean that.
What? This is 2000, you can't see that.
This is
2008.
2008, you can't do that?
1960s, you can do
I stopped doing it in the 1960s, that's right. But I stopped doing almost everything interesting in the Yeah, so where were we? We were talking about charge flow, and the first concept is charge density. Now, density is not the motion of charge, it's just a local version of the idea of how much charge is there. Local means it's identified with a small region of space. There's the idea of charge density. Charge density is just locally, at some particular location, the charge per unit volume that's present. Now, to define it precisely, we do a little bit of calculus and a little bit of limiting notions. We take a little box surrounding a point. We take the total charge in that box. Let's say the box is of size epsilon. It has a volume, epsilon cubed. We take the charge inside that box. What's a good name for charge? Q. Q is the standard terminology for electric charge. Q, inside the box, this is not Q of the world, this is Q of the box. We divide it by the volume of the box, and then we take the limit in which epsilon goes to 0, and of course also Q goes to 0. We take the limit of Q over epsilon as the box gets smaller and smaller, and that's called rho. Rho for density. I don't know why it's called rho and not D or delta or something else, but it's rho for density, and it depends on position. Of course, it also depends on time. The density of charge can change with time, so whatever rho is, it depends on position and time. Okay. What do we do with rho? Well, if we know rho, we can say how much charge is in any region of space. In any region of space, let's take an arbitrary region of space now, with any shape, whatever, then the amount of charge in there, let's also call it Q, but it doesn't stand for the charge in a box now, it stands for the charge in a general region, is then equal to the integral over that region, let's call it d3x, meaning dx, dy, dz, over that region, over the interior of that region of rho. And strictly speaking, we could take this to be the definition of charge density. It's the thing that you sum up or integrate over a region of space to find out how much charge is in there. The total charge in the universe, you integrate over everything in the world, and all of volume, and that gives you the total charge in the universe, but usually that's a fairly useless concept, the total charge in the universe. Better integrate over the region of the laboratory, and that will tell you how much charge is in your laboratory. Now, next concept, the flow of charge. The flow of charge is defined by a thing called the current. You used to thinking about currents flowing through wires. We don't have to be thinking about currents flowing through wires. We're thinking about charges flowing through space, clouds of charge flowing through space. And to quantify the idea of a current, we take a little area. Now this is an area in space, a little square. And we stand there and watch that square and watch the charge passing through that little square. It's a little window. Think of it as a window, small window. And charges go from one side of the window, through the window, out to the other side of the window. And we can ask how much charge goes through the window per unit time. We can wait 1 second and see how much charge goes through the window, take that charge and divide it by the 1 second. But we can also do calculus, and we can go to the limit of a very small time interval. I think that's the last time I will say that we'll take limits. We'll just imagine, you know how to take limits. We study the amount of charge that goes through the window per unit time. Okay? Now that's not yet the current. The amount of charge that will go through that window will not only be proportional to the time element, the little time that you allow, but it'll also be proportional to something else. What is it? The area of the window. The bigger the area of the window, the more charge will go through. So if we take the charge that goes through the window, again, let's call it Q, and divide it by the area of the window, let's call it A, and the little time interval, what shall we call it, delta t? The little time interval, and then take the limit as the window gets small and as the time interval gets small, then we call that object the local current at that point, the point at the center of the window there. But it's a particular component of the current. The current is not a scalar under rotations, with respect to rotations of space, not with respect to space-time, but with respect to rotations of space. The charge is a scalar. The amount of charge in a little region doesn't matter which orientation you draw. But the flow of charge is more like wind velocity. It has a direction associated with it. So for example, if the charge happened to be flowing along the x-axis here, and we took our window to be in the yz plane, to be in the window along the blackboard here, no charge would go through that window. It's like a wind blowing, here's a window, and the wind is blowing in this direction, no wind goes through the window, but if you turn the window so that it's facing into the wind, then wind goes through the window. Charge current. Current is a vector, a three-dimensional vector, a vector in the sense of three-dimensional space. And if we orient our window so that the perpendicular to it, let's draw the perpendicular to it, draw a perpendicular. Let's say the perpendicular then is along the x-axis. Right? Then the amount of charge going through, we'll call this an x window, an x-oriented window. An x-oriented window, and remember the x-axis is perpendicular to the window, an x-oriented window, and we take the charge through the x-oriented window per unit area per unit time, that becomes the x component of the charge current. So that's called J. It's called J. Again, J for current. I don't know why J is used.
Is that usually called current density?
Sometimes called current density. Yeah. 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 Sometimes called, yeah. Right. Okay. So in elementary physics, the current is the current through the wire. In advanced physics, it becomes the current density. And in super advanced physics, we forget the word density and we just call it the current again. Right. Right. Yeah. Right. Right. So, in fact, we will even come to a terminology where we will call the complex of J together with rho. We'll just call that the current eventually, but for the moment, yeah, we would just call this the x component of current. And once you hear that it's a component, you know it's a vector, and that's a clue that it's the current density. It's a current density, Jx. Incidentally, the symbol for the current through a wire is I, not J. Okay, so J is the current density. And again, it's a thing that you integrate. You integrate it over time and over the little area of the window to find out how much total charge flows through in a given time. All right.
Capital J or small?
I call it small j.
But the I would not be?
It depends. It depends. Sometimes in some books it's capital I, in some books it's small I. I've seen both. Okay, so that's Jx, and of course there's Jy and Jz. What is Jy and Jz? You take your window oriented along the y-axis, and you ask, notice incidentally that there's a sense of orientation to this window. We're talking about the charge that flows from the left to the right. In other words, the charge that flows along the positive x-axis, from the negative to the positive x-axis. In the same way, we can define Jy and Jz. Jy would correspond to a window oriented along the y-axis, and we would be talking about the amount of charge per unit time that flows from the negative y to the positive y regions, and likewise Jz. All right. Now, what I maintain is that any time current disappears out of the room, there will be on the boundary of the room, what did I say? That when current disappears, charge disappears. If charge disappears out of the room, there will be a current on the boundary. Okay? And the current on the boundary will exactly compensate the amount of charge that flows through the boundaries will exactly compensate for the amount that the charge changes within the room. Let's see if we can quantify that and make an equation out of it. Let's take a little box. It has 6 faces. It's a little cube. It has 6 faces, and let's take this to be the x-axis over here. Now let's take a small amount of time, delta t, and ask how much charge, I think we should probably give this a size, epsilon, epsilon, epsilon in every direction. How much charge flows into the box through face number 1 over here? Here's face number 1. How much charge flows into the box in a small interval of time, delta t? Flows into the box through face number 1. Okay? And the answer is going to be Jx at this point. Let's call this point number 1 over here. It's also face number 1. Jx at the center of face number 1 times the area, epsilon squared, times the amount of time delta t. All right, that's how much charge flows into the box per unit time, per unit area, from the left. Now, let's through the x face. Now there's another x face over here. Charge may be flowing out through there. So how much charge flows out through here? It's exactly the same expression. Let's call this face number 2. And let's call the center point also point number 2. What will it be? Notice that if J is positive, that means charge is flowing into the box. It's flowing this way. If J is positive over here, it means charge is flowing out of the box. So we should subtract Jx at point 2, I hear the right answer, times the same factor. Same area, same time interval. So the answer is, let's write the answer, Jx at 1 minus Jx at 2. That's the change in charge inside the box. But wait a minute, that's not all of it. That's only the stuff that flew in through the X windows. What about the Y windows? Well, same kind of thing. Y window down here can emit charge if the current is positive. If the Y component of the current is positive, charge will flow into the box from the bottom, and it will flow out of the box from the top. And so there's another term. Let's call the bottom face here 3, and the top face 4, IV, 4. And also the centers we'll call point 3 and point 4. Okay, the area of the bottom and top faces are the same. The unit of time is the same. And so what are we going to get? We're going to get Jy of 3 minus Jy of 4. That's the charge flowing in from 3 and out from 4. And then there's the last one. The one flowing in, well, I'm not sure which way the z-axis goes. The z-axis comes out of the blackboard? Yeah, well, I think so. All right, so we add this. This is the stuff that flows in the x direction. This is the stuff that flows in the y direction. And finally, the last term is, let's put it over here, plus, the delta t times epsilon multiplies everything. The last term you can guess, it's going to be Jz. Now, we have to name the well, it's a jz. It's, again, the difference of jc, let's call it at 5 minus jz at 6. What is that? That's the change in charge. That's the amount of charge that flowed into the box. Now, imagine the box is small. We're going to imagine the box is small. Epsilon is going to be small in a minute. What is that equal to? Well, as I said, that's equal to the increase in charge. That's equal to the increase in charge. So that must, in fact, if we divide it by delta t, it's the time rate of change of charge in the box. The time rate of change in the box, of charge in the box. So that's d by dt of the charge in the box, Q, equal to time rate of change of the charge inside the box. The stuff that flew in minus the stuff that flew out gives us the rate of change of the charge in the box. Okay, now, this j of 1 minus j of 2, the distance between 1 and 2 is going to be shrunk to 0. We're going to take this little box and make it smaller and smaller. The difference between j at point 1 and j at point 2 is just going to turn into some kind of derivative. Just the derivative of j between two neighboring points. The difference between a quantity at two neighboring points, what is it? Let's write an equation over here. J of 1 minus jx of 2. That's equal to the derivative of jx with respect to x. Not quite, there's a minus sign here. It's j of 1, 1 is slightly to the left of 2. J of 1 minus j of 2 would be the derivative of j with respect to x, but of course we'd want to divide that by epsilon to make a real derivative out of it. Okay? Yeah, we're going to get epsilon cubed, that's right. So, right, that's right. So this really can be reinterpreted as, let's just reinterpret it over here, epsilon squared. Now, I'm going to want to put an epsilon downstairs. So let's put an epsilon downstairs, and just as Michael said, if we put an epsilon downstairs, we've got to compensate by an epsilon upstairs. Well, that's kind of neat. This is the volume, epsilon cubed. That's going to play a nice role. Keep in mind the volume over here, and then some derivatives of j. What's it going to be? It's going to be epsilon cubed, and three terms. The derivative of jx with respect to x, plus the derivative of jy with respect to y, plus the derivative of jz with respect to z, and I think I have an overall minus sign. What is that? That's the time rate of change, dq by dt. Now, let's divide by epsilon cubed. If we divide this by epsilon cubed, let's divide it by epsilon cubed, q over epsilon cubed. Q is the charge in the box. Epsilon is the epsilon cubed is the volume of the box. What is q over epsilon? Q over epsilon cubed. The charge density, right? So, and this derivative, of course, means standing at the same point. We stay in the same box. We're not moving around as we're doing this. So that really means the partial derivative of the density with respect to time. Partial derivative because we're keeping the positions fixed. So the right-hand side just becomes the partial derivative with respect to time of the charge density. Yeah, minus sign is correct. If I transfer what's in the bracket over to the right-hand side, or put everything on the same side, then I get an equation It's called the continuity equation. And what it says is the time rate of change of density plus the divergence of the current. For those who know what a divergence is, this is the divergence of the current. I'll write it out explicitly. dx jx. Let's call it d by dx. I said I would write it explicitly, and I will. Plus dy jy. No, explicitly.
Isn't that sometimes written just J?
Wait just a second. Plus dz jz equals 0. Say it again.
Isn't, sometimes that's just written just J, dj, the divergence of J.
Yeah, del dot j.
Without any subscripts on the current.
Del dot j.
Yeah, del dot J.
Right. Well, we think of this as, right. Right. So we could write this as, we could also write it as rho dot if I wanted to save myself some symbols, plus del dot j is equal to 0. What does that express? That expresses the fact that the only way that the charge can change in there is by charge flowing into or out of the system. It doesn't change by itself. In other words, if there's no current through the walls, the charge doesn't change in here. It relates the change in charge to the flow through the boundary. That's the deep concept of conservation, deep and useful concept of conservation, that the time, oh, and we can, let's see, why don't I put everything on the same side? If I brought all of this to the right-hand side, it would all be pluses, right? So I think we can do that efficiently by just putting d rho by dt over here and adding plus over here. We're getting rid of brackets and setting the right-hand side equal to 0. Now, this has an interesting look to it. Let me write this in a rather... No minus sign in this equation. The minus sign got eaten up by transposing. Well, when I transposed the d rho dt to the left-hand side, it picked up a minus, and then I multiplied the whole equation by minus. Okay. Let's make up a new notation. What's that?
J sub t?
Yeah. Right. Well, except that we're going to change it a little bit. We're going to call rho j super t, not sub t. Or remember that sometimes we think of t, x, y, and z as x0, x1, x2, and x3. Let's use that notation. And we combine these all together and call them x mu. Now we're talking relativity, and we're talking about 4 vectors and all that kind of stuff. All right, so let's call rho, let's call it j naught. It looks like it's got something to do with time. It does. Let's call jx, the thing that I've called jx. Let's now think of it as an object with an upper index. So I'm sorry I defined it this way. I should have defined it with an upper index. I would not have had to switch in the middle of this argument. Let's just define it everywhere as the same quantity with the indices. Now it's just pure notation. There's nothing, no content to it. I've just changed my notation slightly. Same thing for z. Same thing for z.
But we already learned through that before, where what we used to think of as lower indices turn out to be the things that we want to be upper indices.
With a sign change. Where we change the sign of the time component.
Right.
Yeah, yeah. But now it's just definition. Now it's just definition. Jx, Jy, and Jz with the upper index are exactly the things which I previously should have defined in the first place as having upper indices. I didn't realize that while I was preparing my notes, but I should have. All right. So we take these 4 objects, rho, Jx, Jy, and Jz, And we can now write this whole equation in the compact form derivative sub mu, the derivative with respect to x mu of j super mu equals 0. All right, the first term is derivative with respect to x naught. That means derivative with respect to time of j naught. That's this one. And then when mu is 1, we have the derivative of the x component of j with respect to x, and so forth. This, of course, is summed over mu, but I'm using the Einstein summation convention now. And it becomes quite clear that j mu is a 4-vector. J mu is a 4-vector. I won't prove that, but it does transform as a 4-vector, and it's pretty darn clear from this equation that this equation wouldn't make sense in every frame of reference. The derivation of the argument did not depend on what frame of reference I was in. It was a very general derivation. It must be true in every frame of reference. And the only way that an equation like this can be true in every frame of reference is that if j transforms as a 4-vector, and it does. So we have a new version of conservation in terms of a Lorentz invariant continuity equation. This is called the continuity equation. And it's the powerful principle that basically tells us that charge cannot disappear in one place and reappear in another without flowing through the boundaries of the region. So I could also write this d mu j mu equals 0. Incidentally, it would not change if I put this index upstairs and that index downstairs. You can juggle the indices up and down as long as you keep them balanced. And I won't go through that. But there will be times when equations might come out with one a little differently, with this index upstairs, that index downstairs. It's the same equation. Okay, good. Now let's go back to the derivation from Noether's theorem of the charge density for a simple field theory that had a certain symmetry. I'll just review it for you quickly. It provided for us a concept of a conserved quantity, which I called charge. And in fact, that charge was written as an integral over space. So it's clear that the thing that we define must be the charge density. The question is, does that same theorem provide us, or does something provide us with a notion of J, not of this J, of the space components, of the other components of the current? And so let's go back and review. I wrote down a particular field theory which involved a field with complex valued field. Complex valued field, of course, just means two real fields. So I wrote phi is equal to phi 1 plus I phi 2. Phi star is equal to phi 1 minus I phi 2. And you can just think, if you like, you needn't use this complex notation. The complex notation is notationally neat, but you can just think in terms of phi 1 and phi 2. You can imagine an internal space. This is not real space. This is an imaginary space whose axes are phi 1 and phi 2. And then the value of a field at any point of space, or any point of space-time for that matter, is a dot. Whoops, that's not a very good dot. Is a dot on the plane, phi 1, phi 2, thought of as the complex plane or just the ordinary real plane with two axes. That's the field. If this is phi, then phi star is down here. All right. The symmetry that we're going to imagine is a symmetry under rotating this plane. In other words, let's ask the question, supposing the Lagrangian did not vary, if we rotated the field in this plane, we have to do it everywhere in space simultaneously. So everywhere in space, simultaneously and in time, we rotate the axes of phi. An equivalent thing to do is to multiply the complex phi by a phase factor. One way of describing the rotations of the plane is just to say that phi is replaced by phi times e to the I epsilon, where epsilon could be any real number. In particular, we could take a small real number, and this would just be a small rotation of the axes. So this is one way to describe such a rotation of axes. Another way to describe it, in particular for epsilon small, in other words, just a small angular rotation of the axes, is just to say what happens to phi 1 and phi 2. I'll tell you, let's write the delta phi 1, the change in phi 1, if you just change axes by a little bit, small rotation angle epsilon, what happens to phi 1? It gets changed by amount delta phi 1, which is proportional, I'll just write equal, to phi 2 times epsilon times the small angle. And what about delta phi 2? It's of course proportional to epsilon, but just phi 1? Minus phi 1. Now, how do you look at a Lagrangian and decide whether it's invariant under this operation? Well, in particular, if it's written in complex form. If it's written in complex form, it's really easy. If it contains things like phi star phi in it, that's invariant. Phi star phi doesn't change if you multiply phi by a little phase. At the same time, phi star goes to phi star times e to the minus I epsilon. And so if you multiply phi by phi star, the epsilons will just cancel out. Phi star, which is also incidentally the same as phi 1 squared plus phi 2 squared, phi star phi is invariant. So if the Lagrangian, for example, contained phi star phi, it could contain phi star phi squared. In fact, it can contain any function of phi star phi. This in itself is invariant, and so that would ensure, or this term in a Lagrangian would be invariant. What if it contained things like d mu phi times d mu phi star? Still invariant, because if phi changes by a phase, the derivative of phi changes by exactly the same phase. What about a thing like phi squared? Is that invariant? No, because phi squared, what will happen to phi squared? Phi squared will get e to the 2I epsilon when you multiply phi by e to the I epsilon. Phi star phi, the e to the I epsilons will cancel. Phi squared, they will not cancel. So there are certainly things which are not invariant. If you had something like phi 1 squared plus 3 phi 2 squared, would that be invariant? No. But how about phi 1 squared plus phi 2 squared? Yes. All right, so it's relatively easy to look at a Lagrangian and to see whether it's invariant under this operation. If written in terms of complex notations, then it should involve products of fields times complex conjugates. If it's written in terms of the real components, it should involve sums of squares of things with index 1 and things with index 2. Let's suppose that's the case. Let's suppose that a Lagrangian is invariant. All right. Then there's a symmetry. If there's a symmetry, there's a conservation law. Let's remember the form of such conservation laws. There's a conserved quantity, which is often called capital Q. Sometimes it's even called small q. And the reason it's called capital Q or small q is because it's going to wind up being some sort of charge. So it's related to the thing we've already called charge. But let's just call it Q, sometimes called the Noether charge. Right. What you do is you sum over the whole system. The change, this Q is not the coordinates. It's capital Q, it's a charge. You take the change in the ith coordinate and you multiply it by the ith momentum. Let's call it p sub I. This is the canonical momentum conjugate to q sub I. Typically, delta q sub I will have an epsilon in it, right? Just drop the epsilon. Well, you can leave the epsilon there and then throw it away at the end. We don't need to worry. It's just a numerical multiple, a small numerical multiple of a quantity. We could divide it. We could divide out the epsilon. The epsilon is of no importance whatever. This is the quantity which is conserved. I think the last time I called these delta q's, I think I called them f. I think I wrote that delta q is equal to epsilon times f. Well, that's a redundant notation. Just call it delta q and forget the epsilon at the end of the story. That's the conserved quantity, the sum over all the variables of the canonical momentum multiplied by the small shift in the coordinate when you do the symmetry operation. So now we can write that down very quickly. Q, for our case now, is the integral over space. That replaces sum. What about p sub I? That's the canonical momentum conjugate to phi. There's two of them, phi 1 and phi 2. So we can write pi 1, that's the canonical momentum conjugate to the first field, phi 1, times delta phi 1. What is delta phi 1? It's phi 2. Plus pi 2 times delta phi 1. But that's minus phi 1. Did I say something wrong? I think I did. Minus pi 2 times the change here, which is minus phi 1. That's what Emmy Noether tells us would be the conserved quantity, conserved because of the symmetry. Now, let's go back to the original Lagrangian that we had imagined. The original Lagrangian that we imagined involved time derivatives and space derivatives, but in particular it involved time derivatives. And the time derivatives were in the form d phi by dt squared 1/2. You can forget everything else for the moment. This was the kinetic term in the Lagrangian. Remember what the canonical momentum is. The canonical momentum is the derivative of the Lagrangian with respect to the velocity. Well, that's just the derivative of the Lagrangian with respect to d phi dt, and that's just d phi dt. Pi 1 is d phi 1 by dt. Pi 2 is d phi 2 by dt. And so now we have an expression for the charge. Here it is. Equals integral over space times pi 1, which is, let's just call it phi 1 dot, times phi 2 minus phi 2 dot times phi 1. This quantity must be conserved. We've proved it. We've proved it a dozen times over. We proved it by proving a more general theorem. Here's the more general theorem that this is conserved. This is the conserved quantity, and it's an integral over space. Now, to get a perspective on what this is, on the meaning of it, it's helpful to go back to the analogy with a string. I think we talked about this, but let's do it again. A string or a rope, a jump rope, something like that, stretched between 2 points, free to move around. Our first version of the string was that it was free to move in the vertical plane. Now I want to have it be free also to move in the horizontal plane, not move along the direction of the string, but transverse to the direction of the string, in both directions. Let's call one direction phi 1 and the other direction phi 2. Think of them in a model. We're making up a model of a field theory now. I don't want you to think of a real jump rope. I mean, for the moment, think of a real jump rope. But ultimately, we'll be thinking about mathematical fields describing relativistic field theory and so forth. But for our purposes right now, you can actually think of phi 1 and phi 2 as the x and y coordinates of a point on this string. Now, what is this? What is phi 1 dot? Phi 1 dot is the one component of the velocity. So this is like the one component of the velocity times the other component of position minus vice versa. That should be familiar to many of you as the angular momentum. All right, so if we really think about the mechanical analogy, then the phi dots would be velocities, and of course velocities are proportional to momenta, ordinary momenta now, just ordinary momenta. And this would be like the x component of momentum times y minus the y component of momentum times x. That would be called the angular momentum. The angular momentum about an axis along the string. So think of the jump rope being twirled around. It has some angular momentum. You don't really have to have anybody there twirling. You can just have it anchored to some points, and you give it a whirl, and it continues to whirl, and it doesn't stop unless there's friction, of course. Friction will stop it. But in the absence of friction, it will just continue to whirl around. You can whirl it around with a node so that half of it is over here, the other half is over here, and both of them are whirling around like this. That would be positive angular momentum. Going in the other way would be negative angular momentum. Oh, I could do that. I didn't know if I could do that. I can't do this, though. Right, so that's angular momentum about this axis. That's the analog, that's the analogy for charge. That's the analogy, the mechanical analogy in the jump rope case for charge. But with or without the analogy, this is the expression. Now this can be written another way, another compact way. I'll write it in another compact way. You can write it in terms of the complex components. Let me write it in terms of the complex components. It's also the integral over space, dx, of, I think there's an I, and then there is no phi 1 and phi 2, but phi star dot phi minus phi star phi dot. If you work this out in terms of the components, phi 1 and phi 2, you get exactly the same thing. Notice that the two terms are complex conjugates of each other. And when you subtract, what do you get when you subtract two complex conjugates? Pure imaginary, but if you multiply it by I, it becomes pure real. So you can also write this, if you like. I think there's a factor of 2. There's a factor of 2, if I remember. No, which is not terribly important. If a thing is conserved, then twice it is also conserved. But technically, I think there's a factor of 2 there. We can also write this in another form as just the imaginary part of the integral of phi star dot phi. If you take two things and you subtract a thing from its complex conjugate, it leaves over only the imaginary part. So it's the imaginary part of phi star phi. If you work out, not phi star dot times phi. That's a way to write it. It's a neat, efficient way to write it. And then we can just concentrate on phi dot star phi, and remember at the end that we should take its imaginary part, and that defines the charge for us. All right, it's just a notational device that allows us to avoid writing so many the indices and things, and just write that the charge density is imaginary part of the time derivative of phi star times phi. What about the term with phi dot times phi star? Did I forget to write it? No. When you take the imaginary part of something, you subtract the thing from its complex conjugate. So they're both there. Okay, that's a useful set of notations. Now, our goal is, well, first of all, it's quite clear that this imaginary part of phi star dot phi is the charge density. It's the thing that we integrate over space to get the charge. If this is indeed some sort of charge, if indeed I've accurately identified what this object is and it's some sort of charge, then this thing in here is the charge density, or this thing in here is the charge density, rho.
The sign there, does that matter?
Well, it doesn't really, because you can either define the charge or negative the charge. Somewheres along the line, there was a convention, which I've forgotten right now, but it's strictly a convention of which you call positive and which you call negative, and it really doesn't matter.
Because I'm thinking that there's a minus sign from the left-hand side to the imaginary notation.
That could well be. So could well be. I'm not going to try to track it now. It'll waste time. But it's one sign or the other. And the important fact is that it's not important. It's important to be consistent, but it's not important when you're making your definition of what you want to call charge to fix one sign or the other. You fix a sign and then you stick with it. So let's use this notation with the minus sign here. I hate carrying around the minus sign. Oh, I know what I can do. I can get rid of the minus sign. Yeah, by putting the star on the other side. Yeah, good. Okay, so and this object then, the imaginary part of this object, what is it? It's the charge density. Okay, so let me write down then, we have the following ideas. We have an idea of what the charge density is, and we have the idea of a 4-vector of charge current.
The integrand you're saying is the charge density?
That's correct. The charge density is a thing that you integrate to find the charge. All right, so let's write it down then. Rho, it would be an angular momentum per unit length along the string. Yeah. Right. Angular momentum per unit length along the string, exactly. I think I probably mentioned last time that that this, of course, has an important concept here that is not important now, but will become quite important when we do some quantum mechanics with these ideas. And identifying the charge as being similar to an angular momentum, mathematically, it has the properties of an angular momentum. And you will, of course, remember that in quantum mechanics, angular momentum is quantized. It comes in integer multiples of h bar, positive or negative. That suggests that when we apply quantum mechanics to fields like this, that the charge will be quantized. And indeed it is, for the same mathematical reasons. You don't need to know what those mathematical reasons are. You simply need to know that there's a mathematical similarity, or more than a similarity, an isomorphism between the theory of charge in field theory and the theory of angular momentum to know that, that if one is quantized, the other will be quantized. And that's the origin of the fact that charge comes in multiples of something. And I won't get into quarks, which carry 1/3 of a unit of charge here. This is not the place for it right now. That's a sophisticated subtlety. Okay, so let's see. So where were we? Yeah, currents. Currents. All right, so let's write rho. Rho is the imaginary part of something. And what is that something? Time derivative of phi times phi star. Look at it for a minute and then try to guess what the other components of the 4-vector are. Now notice that this index here is a lower index. A derivative defines first of all, this object, the derivative with respect to t, defines, is it covariant or contravariant? I can't remember. The covariant components of a 4-vector. Phi is assumed to be a scalar field, so this is a covariant component of a 4-vector. And of course, multiplying it by a scalar, it is still the covariant component of a 4-vector. It's pretty obvious what the other components of the covariant components of the 4-vector are. They are just imaginary part of phi star, let's call it all 4 components, d by d mu of phi. That's the completion of the 4-vector. For example, Jx is equal to the imaginary part of phi star dx phi, and so forth. What about the upper components? What about the contravariant components? What is J super x? Same thing. But what about J super t? A minus sign. Okay. We could take all of that into account by simply inventing a notation which keeps track of the signs by putting the indices upstairs. Now, all this means, a derivative with a superscript there just means change the sign for the time component. So that's just a neat little trick that you can do to keep track of signs. It doesn't change anything. And then we're writing the contravariant components. Covariant, contravariant, they only differ by a sign in the time component.
Does anyone write the star on the bottom?
Say it again?
Just, you want to lower the star, right?
Don't lower stars. But, that actually does have a meaning. So we don't want to fool with it. All right. Now, next step. Can we directly prove that this 4-dimensional vector satisfies the continuity equation? All right. We would like to show that this object does really satisfy the continuity equation. That's where we came in with the continuity equation. And I think we'll take a little break. But at the end, after the break, we will derive the continuity equations from the field equations. You can't get them from nowheres. You've got to get them from somewheres. What do we have? We know some things about how phi moves in space and time, how it varies in space and time. And if we're lucky, it will be enough to prove for us that the continuity equation is satisfied for J. So that'll be the next step. Prove the continuity equation. Notice we really have not proved the continuity equation. What we proved using Noether's theorem is the conservation law. All that really tells us is that the total charge in the universe doesn't change with time. We have not really proved the continuity equation. So that's a separate thing to prove, but it is true. So we'll come back to it in about 7 minutes. Okay, our goal is to check the continuity equation. Our goal, I think, is to wait for the remainder of the class to come in first. It does, but I think not for the electron. Yeah, the answer is yes, it has something to do with it, but it is not the same thing. It's something different. We'll get to it. I think we'll be able to talk about isotopic spin. Unfortunately, we have to talk about spinors, which is a subtlety, but we'll try. We'll try our best. Yeah. So we have a guess for what the 4-dimensional 4-vector of current flow is. And the only thing to check, there's only one thing to check, and that's to check that it is conserved, meaning to say that it satisfies continuity equation. These days, when a physicist says something is conserved, He literally means that the current, number one, that there is a notion of current and charge density, or density of whatever the quantity is, number one, and that it satisfies the continuity equation. Continuity equation is always central to what a physicist means by saying something is conserved. Okay, so we ought to then check the continuity equation. Now, the continuity equation has to do with the way the components of J vary in space and time. We're going to differentiate them after all. And that in turn has to do with the way phi varies in space and time. What is it which controls the way that it varies with space and time? The field equations. So in order to write some field equations, let's begin with a simple Lagrangian. We're not going to do this for every possible Lagrangian, although we should. And it would be true for every Lagrangian of the right form with the right symmetry. But let's take a particular Lagrangian. Our favorite that we've used over and over again, Lagrange density equal to phi dot, let's say phi dot squared over 2 minus the space derivatives of phi squared. Same thing for y and z over 2. And then let's add what I have been calling a mass term, just for fun. This is phi squared. I'm sorry, I withdraw this. It's phi star dot phi dot no 2. Star dx phi star. Now remember, you can write this in terms of usual components, phi 1 and phi 2, and it's just the two Lagrangians, one for each component of the field. And then I want to add something just for fun, or just for a little bit more completeness. Let's see, do I want minus or plus minus? Minus mu squared, where mu is just a real number, times phi star phi. I don't, in previous lectures, I might have just called this mu, I don't remember. X, Y, and Z, all of them.
Is that a mu?
It's not, it's just an X and a Y and a Z. But we can write the whole thing. We can write the whole thing in the form d mu phi, d mu phi star. That's all it is.
Well, you have L equals phi star phi. Is that a mu one? I can't.
Here?
No, just the left.
First one.
Here.
What is that?
It's phi star dot,
Phi star dot.
And then what's what?
Phi dot.
phi dot.
Oh, okay.
Yeah.
You get two stars in the middle term if you want for
Oh, it's 2 stars in the middle term. Sorry. Good. 1 star in the middle term. All right. I only write it in this form to just display the obvious symmetry that it contains things times their complex conjugates, and so it has this symmetry that, that we've been talking about. All right. The important thing is the field equations which follow from this. So, oh, there should be a 2 over here. The 2's are not important. No 2 there. No 2. Okay. The important thing is the field equation which follows from this. The field equation is just, we've written it before. Without the mu squared term, just let's write it out explicitly. The second derivative with respect to time of phi minus the second derivative with respect to x, y, and z. I'm just going to include x, but we also have a term for y and z, phi. And then from here, let's see, I think there's either a plus or a minus. Plus, I think. Plus mu squared phi equals 0. This, without the mu squared, it would just be the usual wave equation that we've written down many times. We make it into 3-dimensional wave equation by putting a y and a z term, adding them in. And then this mu squared term is just another term that's I'm including for completeness or semi-completeness, just to have it there. We'll use it later. We'll study it later. It plays some important role in the mass of a particle. But for the moment, it's just an extra term I threw in to be a little more complete. Okay, here's our field equation. Now, I can write it in a very compact form. It is d super mu, d sub mu phi, either plus or minus. Let me get this right. I think minus mu squared phi equals 0. So this is a nice compact form for it. And it stands for the second derivative with respect to time minus the second derivative with respect to space. Okay, that's our field equation. What we want to derive from this field equation is the continuity equation for J. So let's write the continuity equation for J and see if it follows. The continuity equation for J is d mu j mu equals 0. So let's just do it. If it's true, then it means that. This is what it would mean. It means the imaginary part of d mu on phi star d mu phi equals 0. That's what it would mean. J, here's J, the imaginary part anyway. We differentiate it and set it equal to 0. Well, I'm not saying it's true. I'm saying, is it true? Not it is true, but is it true? Okay, let's check it. Let's follow it through a little bit. It's the same thing as, now I can differentiate. I can write that this is the imaginary part. And the derivative here consists of two terms. In one term, the d mu hits the phi star. In the other term, the d mu hits the derivative. All right, so what does it got? We have two terms then. We have d mu phi star, d mu phi. That's when the derivative hits the phi star. Then we have plus phi star d mu phi. Does this or does this not equal 0? That's our question. So let's look at it. First thing is, this is real. It consists of things like the time derivative of phi star times the time derivative of phi. Things times their own complex conjugates with various signs. The signs don't turn something real into imaginary. So this is pure real, and its imaginary part is just 0. Good, that was fast. We got rid of that fast. This piece here is clearly related to the field equation. Where's the field equation? The field equation has exactly that same thing in it, d mu phi, and it's equal to mu squared phi. By virtue of the field equations, this becomes equal to the imaginary part of phi star. Now, d mu phi, that's mu squared phi, plus or minus. I don't know, plus or minus, whichever. But this is just phi star phi. Mu is real. Phi star phi is real. Yeah.
Am I just confused, or you're using mu ambiguous?
Oh, I'm sorry. Very good. Yes, I've used mu for two different things. Index, and let's call it m. Let's call it m. It is connected with the mass of a particle, but it differs from the mass of a particle described as a quantum of the field by a factor of h bar. That's why I didn't want to call it m, but never mind. I don't want to. You are right. H bar is equal to 1. M squared. Yes, but of course, since we're doing classical physics, that means h bar is equal to 0. So.
Well, all the stronger then.
Yeah. But phi star phi is also real, pure real, and so this is also 0. So the whole damn thing is 0. The whole thing is 0. But not as an identity, but by virtue of the field equations, by virtue of setting this thing equal to this thing, that's the field equations. In other words, for any solution of the equations of motion, not for any old phi that you can write down, but for any phi which satisfies the equations of motion, this derivative d mu j mu is equal to 0. Again, I'll repeat why. This is real. Its imaginary part is 0. This is not obviously real, but the equations of motion tell us that it's equal to phi star m squared phi. One phi star comes from here. The other phi comes from the equation of motion. So the continuity equation is indeed satisfied. So that's, that in itself doesn't establish that this is the electric charge of anything. What it is the electric charge of the assembly of charged particles that might be the quanta of the phi field. But it doesn't prove that this is charge. What it does is it makes this a candidate. It's a conserved quantity, a quantity which satisfies a continuity equation, and it makes it a possible candidate for a mathematical description of charge. And we're not going to go more deeply into that right now.
Well, isn't that enough to say it's a sum quantity or something?
It's, yes. Yes, if we knew a little more, I would make a more complete argument. But for the moment, it just establishes it as a candidate for an interesting quantity that's conserved, that satisfies a continuity equation. And among such quantities in physics are electric charge. Now, we'll come back to this. You asked me about isotopic spin. I'll tell you very quickly. Isotopic spin, of course, has to do with nuclear physics, and it's connected with all of this, but I'll just tell you very quickly. We imagined a theory here in which the field had two components, phi 1 and phi 2. And the symmetry was an invariance with respect to rotation in the plane. In a theory of isotopic spin, which is not a theory of electric charge, or it can be partly a theory, but the theory of isotopic spin is just basically a theory with three components in which there are three axes to the fields which are rotationally invariant in 3 dimensions. Internal dimensions, not real dimensions, but internal dimensions. And otherwise is extremely similar to this. So the pattern would be the same. What happens to angular momentum in 3-dimensional world? Angular momentum, if there's only 2 axes, is either plus or minus, goes this way or goes this way. What about angular momentum when you're in a 3-dimensional world? It becomes a vector, which means it has 3 components. Right, 3 distinct components, any one of which could be positive or negative. And the isotopic spin is a thing which has 3 distinct components. And so in a certain sense, it describes 3 charges, not just 1 charge. But let's not... All right, I want to talk a little more about energy and momentum in relativity and its connection in particular with mass and its connection with this guy over here. I don't think we'll get to the full story tonight. We'll continue it next time. But I want to get to the story. I want to go back to ordinary special relativity. Let's forget field theory, and let's talk about the motion of particles in ordinary relativity theory, and identify in ordinary relativity theory the energy and momentum of a particle. Oh, I know how we can do this. We can do this by the method of Lagrangians. However, we won't. Maybe next time. On further reflection, I think I won't. All right. There's a concept of momentum in non-relativistic physics. It's mass times velocity. The concept of momentum in relativistic physics is also mass times velocity. Those of you who have taken my class previously in relativity and things would know that it's not mass times ordinary velocity, but it's mass times 4 velocity. The ordinary velocity is the components of a 3 vector, mass times, what am I saying? Ordinary momentum is a component of a 3 vector, and that 3 vector involves the 3 vector of velocity. The 3 vector of velocity is the 3 components of spatial position, their derivative with respect to time. In other words, dx dt, dy dt, and dz dt. Let's just write dx dt as one of them. The 4 vector of velocity is a 4 vector, and it's the derivative not with respect to ordinary time, but with respect to proper time. Let's call it tau. It has 4 components, including a time component. So there's a notion of the time component of velocity, and the velocity forms a 4 vector. Now this is obviously a 4 vector. Tau is proper time. It's invariant. It's a scalar. X is a vector, or dx is a vector, and so this is a 4 vector. But before we go on, let me remind you what d tau is. D tau is a thing whose square is dt squared minus dx squared. Minus dy squared minus dy squared minus. I need a notion for the square of 3 vectors. I need a notation for the square of 3 vectors. Let's just call it dx vector squared, like that. It stands for dx squared, dy squared, and dz squared. That's d tau squared. Now there's some speeds of light in there. Where do the speeds of light go? I think I usually like to put them here. Some people like to put it in front of the dt squared, but then d tau doesn't have the same units as dt. And so proper time and time don't have the same units. I want proper time and time to have the same units. So I put the c squared down here. And then, since c is 1 and 1 is 0 and, no. Let's just, I'll tell you where the c's go when it's important to know where the c's go. But for the moment, c is equal to 1. All right, this is d tau squared. D tau is, of course, square root of dt squared minus dx squared. But now let's divide and multiply by dt. Let's put a dt here and a dt here. Now, I've done nothing, but now I want to bring the denominator dt into the square root. To do so, I have to square it. Okay, dt squared over t squared, what is that? dt squared over dt squared, that's 1. 1. Now, what is dx squared, or dx vector squared, divided by dt squared? 3-dimensional square of the 3-dimensional velocity, minus v vector squared. 1 minus v squared. Since I'm squaring it, I don't even have to put the, it just means by definition the sums of the squares. Good. Now where would the speed of light go in this formula? Under the v. V squared over c squared. That means for ordinary velocities, let's put it in for the moment, for ordinary velocities small by comparison with the speed of light, d tau and dt are almost the same thing. They're almost the same thing to within a very, very small correction. But for velocities up near the speed of light, it's pretty important. Let's write this one other way. d tau divided by dt, or better yet, dt divided by d tau is equal to 1 divided by the square root of 1 minus v squared over c squared. And let's just, we'll put back the c when we need it for various purposes.
Don't you have a, isn't it DTC on the outside?
No,
How is
no,
D-
no.
To put the C inside, you had to put a C outside.
No, I'm not, no, it's right, it's right. To restore the units, I realized that tau and t have exactly the same units. So I can't put a c out here. That would change the units of the left-hand side and the right-hand side. But v, by itself, 1 has no units. 1 is dimensionless, and so v squared over c squared has to be dimensionless. So that means it's the ratio of v to c. It's right. Okay. Yeah. Good. Now let's compute the various components of the 4 velocity. The first component of the 4 velocity, or the 0th component, is dt by d tau. And here it is. 1 over the square root of 1 minus v squared over c squared, but I'll leave that. Now what about the x component? The x component is dx by d tau, but let's write that as dx by dt times dt by d tau. But what is dt by d tau? It's 1 over the square root of 1 minus v squared. So that means, let's write the equation. Let's write the equation properly. dx by d tau is equal to dx by dt times dt by d tau, which is the same 1 over square root of 1 minus v squared. But what is dx by dt? That's just the x component of the velocity, vx. All right, let's put back the c squares. The only place there's a c squared is over here. 1 minus v squared over c squared is where the c's go. Also over here. These are now the components of a 4 vector. Well, these are the first 2 components of a 4 vector. The other components would involve a vy and a vz. So here's our 4 vector. The x mu by d tau consists of 1 over the square root of 1 minus v squared and v over the square root of 1 minus v squared. That's our 4 vector. 1 component over here, and then 3 more components over here. Now let's move on to momentum. Momentum in non-relativistic physics is just mass times velocity. Velocity means ordinarily dx by dt. It's not a very good quantity from the point of view of relativistic physics. It doesn't have a distinct transformation property. It's dx by d tau that has the good transformation property. So it was Einstein's guess, and then he confirmed that guess by various Gedanken experiments, that when you go from Newton to special relativity, you should replace mv, or m dx by dt, by m dx by d tau. And that would wind up being the momentum, the x component of momentum of a particle. Now, just the usual 3 components of momentum. All right, so what does that mean now? Here is dx by d tau, and what it says then is that this is equal to the mass times the velocity, here's the 3 components, divided by square root of 1 minus v squared. Now, as Einstein made the guess based on his rule that everything should have distinct and good transformation properties under Lorentz transformations, that the momentum of ordinary non-relativistic physics would get corrected by a factor of square root of 1 minus v squared in the denominator. The very small correction when v is small, especially when v over c is small, a very small correction, not worth very much when the velocity of an object is small. It gets a little bit sick when you get up near the speed of light. When v gets up near the speed of light, you get a denominator which gets closer and closer to 0, so the momentum gets very much bigger than just mass times velocity. But that's okay. This was his formula, and it is the correct formula. Now, the question is, what is the 4th component? The 4th component here was something new. The 4th component would be m times dt by d tau. And that's just the mass Let's call it P naught, the time component of the momentum, whatever that means. And that will wind up being just the mass divided by the square root of 1 minus v squared over c squared. That's just multiplying the mass by dt by d tau. So Einstein said, what is this thing? And he realized very quickly that it was just the kinetic energy of the particle. It was the kinetic energy, and that indeed, just as with Newtonian physics, a free particle would have 4 conservation laws, 3 of momentum and 1 of energy. Okay. Now, if it's not quite right, the factors of C aren't quite in the right place to define conventional units of energy. What do I have to do to get conventional units of energy in there? Hmm? 2 powers of C in the numerator. So let's if I call it P naught, this is correct. But if I want to identify that with energy, I have to write that there's another factor of C squared, mc squared divided by square root of 1 minus v squared over c squared. All right, so for particle at rest, v equals 0, its energy is mc squared. And the fact there's a c squared here, that's a convention, or it just makes it consistent with non-relativistic units, but let's leave it there. E is equal to mc squared over the square root of 1 minus v squared over c squared. But basically, what it is the time component of a 4 vector, which is composed out of the mass times the 4 velocity. That's energy and momentum. Shall we work out that what this? Let's work out a little further. Let's calculate what this is when v over c is very small. When v over c, we use the binomial theorem. The thing that's in the denominator is 1 minus v squared over c squared to the minus 1/2 power, all times mc squared. Now, anybody remember the binomial theorem well enough to expand this out? One plus 1/2 v squared over c squared, plus higher orders. This is equal to 1 plus v squared over 2c squared, all times mc squared. That's the expansion of this. Remember that v over c is very small. V squared over c squared is very small. And if you expand it in powers of v squared over c squared, the first correction to 1 starts with 1, then v squared over 2c squared, and then things which are truly incredibly small, v to the 4th over c to the 4th, those are really, really small. Much smaller than this. Now, what does this give us? This gives us mc squared. That's good old famous Einstein mc squared, plus the mass times v squared over 2, and the c squares cancel. C squared in the denominator and c squared in the numerator. Okay, so what do we get? We get mc squared, the rest energy of a particle, plus the ordinary kinetic energy. Of course, this was the first indication of Einstein's idea of E equals mc squared for an object at rest. For an object at rest, E equals mc squared. And then the first correction is mv squared over 2. And the higher corrections involve much. Notice that the c's cancel out of here. The next corrections would truly be small by a diminishing factors of 1 over c squared. Okay, I just wanted to make sure that we understood.
The first m is not the proper mass, I guess.
It is the proper mass. It's the rest mass. This m?
Yeah.
Yeah, it's just, look, physicists don't even use the term rest mass anymore.
Okay.
The term rest mass hasn't been used for 75 years. Only in elementary physics classes are the only place where the term, and even there I don't
Or
think.
it's their goal to mislead you.
Right. The mass of the particle is a property of the particle which doesn't care whether the particle is moving or not. And it is the energy of the particle when, or the energy of an object when the center of mass of that object is at rest. That's the definition of a mass. Take an object, it could be a pot of hot water, it could be whatever it happens to be, put it at rest, which means make sure that its total momentum is equal to 0. Whatever its energy is called its mass within a factor of c squared. Okay, so m means rest mass. I will never ever talk about rest mass or moving mass. We'll just talk about mass, and it means what used to be called 10,000 years ago, used to be called the rest mass. Right. Anyway, this is energy and momentum. Now, it's kind of interesting. You get into some very peculiar mess when you try to think about particles whose mass is 0, looks like their energy is 0, but the problem is when a particle has 0 mass, it also moves with the speed of light, and so the denominator is also 0. You get into a nasty 0 over 0 situation. You can see that most clearly, in fact, from the momentum. Well, let's concentrate on the energy. Both the energy and the momentum have peculiar things that happen when the velocity goes to the speed of light. Okay? When the velocity goes to the speed of light, the denominator goes to 0, and we don't like denominators which are equal to 0. So it's not a good idea to try to study the limit of massless particles with these equations. But there's another thing we can do. Instead of looking at the relationship between energy and velocity and mass and velocity, get the velocity out of it altogether and just look at the relationship between momentum and energy. This is where we're going. I want, for future purposes, to have the relationship of the energy to the momentum for a particle of mass m, without having to worry about what its velocity is. All right, so all we have to do, let's see, where are we? Let's write them down over here and find the relationship between them. Incidentally, that relationship for non-relativistic physics would just be energy, kinetic energy in particular, is momentum squared divided by twice the mass. We might also throw in mc squared, but this is the analog of what we're looking for, relation between energy and momentum. What does that look like in the theory of relativity? Okay, so here we have it. We have energy equals m divided by square root of 1 minus v squared. I'll put the c's back. I don't like carrying them around. I get confused. And p is equal to mv over square root of 1 minus v squared. Okay, the square roots in the denominator are a nuisance. So to get rid of them, let's figure out what e squared is in terms of p squared. Instead of figuring out e in terms of p, let's get e squared in terms of p squared. That'll get rid of the square roots in the denominator. So e squared is m squared over 1 minus v squared. And p squared is m squared v squared over square root of 1 minus v squared. No square root. 1 minus v squared. Well, I could solve for v. What I could do something complicated. I could solve for v squared from this equation and then plug it into here. And that would give me the energy in terms of the momentum, or the momentum in terms of the energy. But it's easier to do than that. All we have to do is take the difference of these two. Let's take the difference of these two. E squared minus p squared. Let's see what we get. In the denominator, we're going to get 1 minus v squared, because both terms have the same denominator. Both terms also have m squared. And then this term has 1, And this term has minus v squared. So 1 minus v squared. Well, that's lucky. Just e squared minus p squared equals m squared. Now, that's not so surprising. E and p are components of a 4-vector. The invariant that you make out of a 4-vector is the difference of the squares of the time components and the space components. Okay? Here's what we have. We found the difference of the squares of the time components and the space components are the square of the mass. In other words, the mass is simply the invariant that you make from the 4-vector of energy and momentum. That's another way to think about it. If you have a 4-vector of energy and momentum, then the invariant length of that 4-vector is the mass. Another way to say it, if the momentum happens to be 0, then E and M are the same thing. Okay. Now let's see if we can figure out where the C's go. This is pure dimensional analysis. Where do you want to put it? You want to put it here? Numerator or denominator? Numerator. C squared here. I'll tell you how I know in a minute. C squared here and C to the 4th here. Now, how do I know that? First of all, let's forget this term. E squared, if E equals mc squared, E squared must be m squared c to the 4th. So that makes sense. Now, energy is typically momentum times velocity. Even in Newtonian physics, mv squared, which is mv squared is velocity times momentum. So in energy, this is just unit-wise. mv squared has units of energy, velocity times momentum. So energy has units of momentum times velocity. That's the basic connection between energy and momentum for a relativistic system, for a relativistic particle. Let's write it just in terms of energy. It says that energy is equal to the square root of momentum squared times c squared plus mass squared times c to the 4th. That's a generalization of, certainly Einstein knew it, but it's a generalization of Einstein's E equals mc squared. E equals square root of m squared c to the 4th, and then if the object is moving, it has momentum, you add p squared c squared to it. Okay? So this is our basic energy-momentum relation. And notice, once we've gone this far, we can now smoothly, with no big problem, take the limit that the mass goes to 0. And in that case, energy is just equal to the square root of p squared c squared, or just the magnitude of the momentum times c. You might have thought that the answer ought to be, well, let's see, non-relativistically. What's the answer non-relativistically? Energy, which is 1/2 mv squared, is equal to velocity is equal to momentum times velocity over 2. You might have taken this equation and said, okay, just plug in velocity equals the speed of light, and you get c times p over 2. Well, you'd be wrong. You'd be wrong by a factor of 2. That's the whole effect of relativity on the formula for a massless particle, or for a particle moving with the speed of light, is that the energy is twice what you might have gotten by just using Newton's equation. Of course, it wouldn't make any sense to use Newton's equations. But PV over 2 is the relation, non-relativistically, PC is the relationship in relativity. All right, I'm not going to use this now. We're going to use it next time to explore the connection between waves and particles and the relationship between the energy of a wave, the momentum of the wave, and the properties of waves, and how those properties of waves are similar to, in fact identical to, these relationships here. Something noticed partly by Einstein, something Einstein and de Broglie, Schrodinger, and so forth. That's not because we're getting into quantum mechanics now. We're simply exploring wave motion and the kinematics and the dynamics of moving waves. But there is a strong sense in which a strong flavor of the relationship between energy and momentum of particles on the one hand and frequency and wave number of waves on the other hand. So that's where we're going next time. Good.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.